and welcome learners. In the current session, we will discuss on the topic measures of central tendency part 2, which is the part of unit 1 of course MST 002 descriptive statistics of PGDST program and unit 5 of course BST CT 131 descriptive statistics and probability theory of BSc General in Statistics program. Myself, Professor MANISH Trivedi, Faculty in Statistics, School of Sciences, IGNOU, New Delhi. In the previous session, Measure of Central Tendency Part 1, we have discussed about the measure of central tendency, arithmetic mean and various method of calculation of arithmetic mean. In the current session, we will discuss some properties of arithmetic mean along with examples. So, as we know that arithmetic mean fulfills most of the properties which being representative figure for the entire data set and expected from good measure of central tendency. First of all, the concept of mean is seen to be scientifically justified, for which it is defined. In almost all type of data, it is seen to represent the nature of different set of data as far as its property of central tendency is considered. The mean possesses many of manipulative properties which makes it applicable in variety of situations. We shall discuss some of such properties and prove them in the coming slides. So, let us start with the first property. The property 1 says the sum of deviations of the values of a set of observations from its mean is always 0. That is, symbolically we can say that summation of xi minus x bar is equal to 0. So, let us assume that x1, x2, x3 up to xn be the observation in the series, then the mean will be x bar equal to sum of an observation, that is x1 plus x2 plus x3 up to xn and divided by the total number of values or the observation, that is small n. So, from this formula we can get the sum of observations, that is x1 plus x2 plus x3 up to xn is equal to n times of the arithmetic mean x bar. So, we have to remember this equation and that will be used in the further manipulations. After taking the deviations of these values and number of values in the data, that is x1, x2, x3 up to xn from the mean value x bar. So, the new observations will be x1 minus x bar, x2 minus x bar, x3 minus x bar up to xn minus x bar. Now, with the help of these new values, if we calculate the new mean, then it will be the sum of all the new values, that is x1 minus x bar plus x2 minus x bar, x3 minus x bar up to xn minus x bar, and we divide this total by the total number of values, that is small n. Now, in the next step we separate all the x bars. So, that will be the sum of all the n number of values separated minus n times of x bar addition and divided by small n. As we have seen in by the formula of the mean, that sum of all the observations is equal to n times x bar. So, we will put the value over here in place of summation of all the values, and n times of x bar will be n times n multiplied by x bar. So, here the same quantity is there in the numerator and that will be cancelled and it will become 0. So, by this derivation we have proved here that if we take the sum of deviations of all the values in the data with respect to its mean, then it will become 0. So, now we take an example to make it more clear, let's we have the 5 values here of x 20, 30, 40, 50 and 60. The sum of all the values is 200, and if we calculate the arithmetic mean, so 200 divided by the number of values 5 is 40. Now in the next column in the table we can see that the deviations of all these 5 values from its mean is minus 20, minus 10, 0, plus 10 and 20, and the addition, or you can say the sum of all the deviations is becomes 0. So it's again we have proved here that if we take the deviations of all the values from its mean and take the sum of all deviation, so that is equal to 0. Now we come to the second property, and the second property says that sum of squares of deviations of a set of observations from arithmetic mean is minimum. That means if we take the sum of squares of deviations of the observations in a series or in a set of data, then it will be minimum in comparison to the sum of squares of deviations taken from any other values in the data. So symbolically we have to prove here that sum of xi minus x bar square is lesser or equal than the sum of squares of deviation from any other value that is assumed as a constant a in the data. So in the next step, right hand side we add and subtract the mean value and expand this square term in the third step. So when squaring the third step, the first step will be summation of xi minus x bar square, that is the same as the left hand side. Second term, that will be sum of x bar minus a square, so that is x bar is a constant, a itself a constant value. So difference of these two constant is a constant, and square term, sum of square terms of these constant value is a constant term. So sum of all the constant terms will be multiplied the how many times it is total, it has been totaled. Third term, that will be 2 times of xi minus x bar multiplied by x bar minus a. So here again x bar minus a is a constant value, so that will be coming out of the bracket in the fourth step. So in fourth step we have got here the 3 part. First part, that is summation of xi minus x bar square plus n times of the constant value, that is x bar minus a square, and in third term, that is 2 times of x bar minus a, that is constant, and summation of xi minus x bar square. And we have already seen in the property 1 that sum of all the deviations of the observations in a set of data from its mean becomes 0. So that term will become 0 and multiplied to the constant quantity 2 times of x bar minus a, that will also be 0. So in fifth step, the summation of xi minus x bar square will be taken to the left hand side. So the same quantity will be cancelled and it will become 0. So in the left hand side it is 0, and the right hand side it only remains the n times of x bar minus a square, that is a positive quantity, because x bar minus a, that is the difference of 2 constant quantity, and a square term will always be positive. So if the last term we have seen in the derivation is true, then we have started from the first term, that is sum of xi minus x bar square is less than or equal to the sum of xi minus a square term is 0. So that means the sum of squares of deviation of a set of observations from arithmetic mean is minimum. Let me take an example to get it more clearly. In the example we have taken the x values 5, 10, 15, 20 and 25. The sum of all the values is 75. We have taken the deviations from the mean. So, the mean is calculated, that is sum of all the values 75 divided by the total number of values 5. So, 15 is the arithmetic mean, and if we take the deviations from arithmetic mean from each and every value, so it is minus 10, minus 5, 0, plus 5 and 10 in the second column. In the third column we take the square of these deviations. So, that will become 100, 25, 0, 25 and 100, and sum of all the squares of deviations is 250. Now, again we take a random value, that is an assumed value 10 from the x values and taken the deviations in the fourth column. So, it will become minus 5, plus 5, 10 and plus 15. If we square these deviations, then sum of squares of deviations from a random value 10 is 25, 0, 25, 100 and 225, and sum of squares of deviations from any other value, that is assumed mean value or a constant value, that is 375. So, here we can see that sum of squares of deviation from the arithmetic mean is lesser than the sum of squares of deviations taken from any other value of the data. Now, we proceed to the third property, and third property says that if every value of the variable x is increased or decreased by a constant value, the arithmetic mean of the observation so obtained also increases or decreases by the same constant. So, let us assume here that x1, x2, x3 up to xn be the observations in a series, then the arithmetic mean will be x bar equal to x1 plus x2 plus x3 up to xn, the sum of all the observations divided by small n, the number of observations. Thus, from here we can see that sum of all the observations x1 plus x2 plus x3 up to xn is equal to n times the arithmetic mean, that is x bar. Now, if we add a constant value p in each and every observations in the series, then the new observations will be x1 plus p, x2 plus p, x3 plus p up to xn plus p. The new mean, if we calculate by using the new observations, so that will be x1 plus p plus x2 plus p plus x3 plus p up to xn plus p, the sum of all the new observations divided by small n. So, in the next step we separate all p values, that will be added n times, and the sum of all the observations x1 plus x2 plus x3 up to xn and divided by small n. Now, from the mean formula we have got the sum of all the observations is equal to n times the arithmetic mean x bar. So, in the next step n times x bar plus n times p divided by small n. So, n will be separated and will be cancelled from the small n, that is in the denominator. So, now the remaining term will is x bar, the arithmetic mean of from the old values, and plus p, the constant. So, that means if we add any constant value to the each and every value of the data, then the mean will also be added by that constant value. Now, again if we subtract a constant value p from each and every observation of the series, the new observations will be x1 minus p, x2 minus p, x3 minus p up to xn minus p, and the new mean will be calculated by the help of the new values, that will be the sum of all the new observations x1 minus p plus x2 minus p plus x3 minus p up to xn minus p divided by small n. In the next step, we separate all the p values, that will be added n times, and the sum of all the observations in the data, that is x1 plus x2 plus x3 up to xn here, and divided by small n. So, in the next step, sum of all the observations minus n times p will be in the numerator and in denominator small n. We have seen from the last slide that sum of all the observations is equal to n times the arithmetic mean. So, we place that value in place of the sum of all the observations, n times x bar minus n times p divided by small n will be there, and n will be separated and cancelled from the small n in the denominator. So, the remaining term will be x bar minus p. So, here we can see that if we subtract a constant value in each and every observations of the series, then the new mean will be the subtracted by that constant from the old mean. Now, let us take the example to understand the previous property. Here 5 observations of the variable we have taken, that is 4, 5, 6, 7 and 8, and the sum of these observation is 30. Now, we obtain another variable by that is by adding a constant value 2 to each and every value of the x variable. So, that is 6, 7, 8, 9 and 10, and the sum of all the y values become 14. Now, again we have obtained a z variable, that is by subtracting a constant value 3 from each and every value of x variable. So, these will be the values of the z variable will be 1, 2, 3, 4 and 5, and sum of all the observations of z variable value is 15. Now, if we calculate here the mean of all these 3 values variables, so the mean of x bar will be 6, mean of y bar is 8 and mean of z bar. And from the property, if we obtain the mean of y bar by adding 2 the constant value in the mean of x bar, it is also 8, and if we subtract a constant value 3 in the mean of x bar, so we can obtain the mean of z bar. So, that means if we add or subtract any constant value from the each and every value of a variable x, then the mean of new values will also be added or subtracted by the same constant value. Now, the next property, property 4, it says that if the value of the variable x is multiplied or divided by a constant, the arithmetic mean of new observations can be obtained by multiplying or dividing the initial arithmetic mean by the same constant. Let x1, x2, x3 up to xn be the observation in a series, then the arithmetic mean will become sum of all the values divided by the total number of values small n. From this formula, we can see that the sum of all the values x1, x2, x3 up to xn is equal to n times of arithmetic mean, that is x bar. If we multiply all the values in the data x1, x2, x3 up to xn by a constant p, then the new observations will be px1, px2, px3 up to pxn. And if we divide the observations in the data x1, x2, x3 up to xn by a constant p, then the new observations will be x1 divided by p, x2 divided by p, x3 divided by p up to xn divided by p. Now, if we calculate the mean from the new observations which have been obtained by multiplying or dividing the observations, then we can see over here that its new mean become the p, that is the constant value, multiplied by the old mean. And next one, if the values, new values we have taken, that is divided by a p constant in each and every observations. So the new mean will become the x bar, that is the old mean, divided by that constant. So here we can see that if we add or subtract it, if we divide or multiply by a constant value to each and every observations in the data, then the new mean will also be divided or multiplied by that constant. Now let us take an example to understand it more clearly. Suppose 2, 6, 8, 4 and 10 are the values of x variable and sum of all the x values is 30. Now if we obtain the new variable y by multiplying a constant 3 in all the values of x variable, so then the value of y becomes 6, 18, 24, 12 and 30 and sum of all the y values is 90. If we obtain again a new variable z by dividing all the values of x variable by 2, then the new value of the variable will become 1, 3, 4, 2 and 5 and the sum of all the z values is 15. If we calculate the arithmetic mean of these three variables, so mean of x is 6, mean of y is 90 divided by 5, that is 18, mean of z is 15 divided by 5, that is 3. Now these values of variable y, mean of variable y and mean of variable z can also be obtained from the property of changing scale that we have already discussed, property 4. So y bar can be obtained by multiplying the constant 3 to the mean of x, that is x bar. So 3 into t, that is 3 multiplied by 6 is equal to 18, and z can be obtained, z bar can be obtained by dividing x bar by 2, that is 6 divided by 2 equal to 3. So that is similar to the means that we have obtained from the data. So it can be said that change of origin and scale affect to the arithmetic value of any data. So if we consider any value, any other variable from changing the origin by adding or subtracting any constant value and changing the scale by dividing or multiplying by any constant value, so the new mean of the new changed variable will be multiplied or divided or added or subtracted by that constant value. So that is also known as the change of origin and scale property of arithmetic mean. Now the property 5 that says if arithmetic mean and the number arithmetic means and the number of observations of 2 or more than 2 groups are known, then we can calculate the combined arithmetic mean of these groups. So the combined mean formula for 2 groups, if we take initially there are 2 groups only, then it will be the combined mean will be equal to the multiplication, the sum of product of the number of observations to the average value of these groups divided by the total number of observations, that is n1 and n2. If we assume over here that n1 and x1 bar are the number of observations and the mean of first group, n2 and x bar number of observations and mean of second group, and x12 bar is the combined mean of both groups. Similarly, this property can be extended up to 3 groups. So, if the numbers and means of these three groups are n1, n2, n3 and x1 bar, x2 bar and x3 bar, so the combined mean x bar 1, 2, 3 will be the sum of the product of the number of observations and means of all these groups divided by the total number of observations, that is sum of observations of these three groups. This property can be extended up to k number of groups also. So, we have an example that mean marks of 120 students in section A is 80, that is given. Mean marks of 80 students in section B is 90. Then we can find the combined mean of both the sections. So, n1 is given 120, n2 is 80, x1 bar 80 and x2 bar 90. So, then combined mean can be calculated by multiplying the number of observations and means of the groups and taking the sum of them. So, 120 into 80 plus 80 into 90 divided by 120 plus 80, that is the total number of observations in both groups. So, after the algebraic manipulations, we can see here that the 84 marks are the average marks of both group, that is combined group. Let us take another example, that is the mean wage of 50 workers in a factory running 2 shifts of 30 and 20 workers is 190. The mean of wage of 30 workers in the morning shift is 200. So, then find the mean wage of 20 workers in the evening shift. That means, if the combined mean and the number of total workers in both shift is given over here and mean of first shift, that is morning shift, is given and the number of workers working in the morning shift and number of workers working in the evening shift is also given, but the average wage of this evening shift workers is not given. So, we have to find that one. So, we put here the values in the formula of combined mean. So, combined mean is given 190, number of workers in the morning shift is 30, average value or the average wage of morning workers is 200, number of workers in the evening shift is given 20, average wage of evening shift is not given. So, we put over here as x2 bar and divided by the number of workers working in both shift, that is 30 plus 20 in the denominator. So, after the algebraic manipulation, we can get over here the x2 bar value is 170. So, we have find over here that the mean wage or average wage of the workers working in the evening shift is rupees 175. So, that we can see over here after the calculating or using the formula of average wage. So, average wage of evening shift we have got, that is rupees 175 rupees. Now, we summarize the session, that in the session we have discussed that arithmetic mean having the most of the characteristics of a good measure of central tendency. Arithmetic mean also possesses some simple but important algebraic properties. The sum of deviations of values of the data from its mean is always 0, that we have discussed in the first property. In the second property, we have discussed that the sum of squares of deviations of a set of observations from arithmetic mean is minimum. If every value of the variable x is increased or decreased by a constant value, so then we have seen that arithmetic mean of the observations so obtained also increases or decreases by the same constant. Similarly, if the value of the variable x is multiplied or divided by a constant, then arithmetic mean of the new observations will also be multiplying or dividing the initial arithmetic mean by the same constant. If the arithmetic means and number of observations of 2 or more groups are known, then we can also calculate the combined arithmetic mean of these groups. Because of these properties, arithmetic mean is one of the most widely used average. Thank you.